Good afternoon, everybody. As I assume this is when you will be watching it. Today starts our third plenary talk, and it will go over how to dissect the equation for power and then how to use that equation. I'm doing it in two parts right now because I'm behind, as I promised you guys last week, the dissecting video, and due to an injury, I was not able to make it. So therefore, we're going to cover how to dissect the equation as well as how to use the equation today. And so, like last time, these things are going to be quick and they're meant for you to watch multiple times. So that way you can learn how to dissect an equation, not necessarily get aid in using I'll scratch that. You're supposed to get help in how to use it as well. So either way, let's get started. An equation that you guys have for this module is for the physical quantity power. And first you got to ask yourself, what is power? So power is a measure of how quickly work is done. It's fairly simple, how quick work is done. So let's take a look at the equation that I have right here. And it says that power is equal to the change in work over the change in time. And that lines up perfectly with the definition of, it's a measure of how quickly work is done. So I guess the next question is, what is work? Well, work is the conversion of energy from different sources. These sources could be potential energy sources or kinetic energy sources. If you want a more formal definition, it's the amount of energy that goes into a force on an object. All right, so we have this definition of power, we have this definition of work, and we've mentioned some other things, potential energy and kinetic energy. So we want to fill out and round out all of these things. So what is potential energy? Well, potential energy is the amount of energy that can be converted to other sources. These sources could be kinetic energy or through energy loss, through processes like friction. So you see here that we are sort of, I picked this equation because it kind of umbrellas all of the topics that you guys are talking about this week in the modules. So I guess that the next question is since we've gone over these three definitions, is what is kinetic energy? Well, kinetic energy is simply the motion, or kinetic energy is the energy of motion. And if you guys go over your the web pages provided by Dr. Breinig for this module, most of these things are defined in greater detail. I just need to tell you guys these little bits so that way we can make it through dissecting this equation. So the whole gimmick behind power and the physical side of it is, by its definition, is how quickly work is done. So if we have some kind of object that maybe we're standing on top of a building on the roof and we want to drop a ball, before we drop that ball is loaded with potential energy. Because the moment that I drop that ball from the roof, gravity is going to take over and it's going to start converting and doing work on this ball, converting that potential energy into kinetic energy. So depending on if how long it takes for the ball to hit the ground, would determine how much power that ball will release when it hits the ground. So let's go ahead and fill in a few more blanks. As we said that power is equal to the change in work over the change in time, which is also equal to work, the final work minus the initial work, divided by the final time minus the initial time. Okay, so let's go ahead and define these things so that way we are thorough. E is power. It has units of joules per second. Which is equivalent to watts. We have delta W, which is just the change in work. And we have delta T, which is the change in time. All right, so I wonder how we can utilize all this. There's not much in this equation in terms of dissecting, so much as there's a load of physical concepts that go behind this. And so what we want to do is we want to learn how we can apply this to a question. And so the question that I have chosen is that the first asteroid to be discovered is Ceres. It is the largest and most massive asteroid in our solar system's asteroid belt, having an estimated mass of 3 times 10 to the 21 kilograms and an orbital speed of 17,900 meters per second. We want to determine the amount of potential energy, and we want to determine the power released if Ceres hit the Earth and upon collision converted all of its potential energy to kinetic energy in 0.5 seconds. Okay, so some things that we're going to need. We're going to need big G, which is Newton's gravitational constant. We're going to need the radius that the asteroid is, or the distance that the asteroid is from Earth, which I took it to be the outer region of the asteroid belt, which is approximately 6.283 times 10 to the 11 meters. We also need to know the mass of our sun, and we're given the mass of the comet and the velocity that it has. So notice what I did here. I went through and I told you, and I've already pre-written down what we need. So where did that come from? Well, we know for a fact that gravitational potential energy is equivalent to GMM over R. Okay. And so these are all of the quantities that I need. We have Newton's gravitational constant. Let me go ahead and be thorough here. We have the mass of the sun right here. And then we have little m, which is the mass of our comet, and this R. Okay, so to answer question A, we want to determine the amount of potential energy. Well, I've given you that equation, and as you can see, that is right here. And all I'm going to do is just start plugging numbers in. So I'm going to take Newton's constant, I'm going to plug it in here. I'm going to take the mass of the sun, I'm going to plug it in here. Take the mass of our comet, plug it here, and the distance. All right, let me get out my calculator. Oh, Okay, so we have 6.67 e to the negative 11 times 1.989 e to the 30 times 3 e to the 21 divided by 6.283 e to the 11. This gives me a potential energy of 6.3345 times 10 to the 29 joules. Okay, so this is immediately our answer to part A. I can be thorough, and let's just put this under here. Okay, and so now we have part B, which says to determine the power released if Ceres hit the Earth and upon collision converted all of its potential energy to kinetic energy in 0.5 seconds. So we're given a time interval, and we're told that all of its potential energy is converted into kinetic energy. So that would mean that it immediately has 6.283 times 10 to the 11. Oh, sorry, wrote down the wrong number. 6.3345 times 10 to the 29 joules. Now, we have the ability, why did I say that? Why did I just immediately say this? The reason why I said this was because of this concept you guys learned about called conservation of energy. And we learned that gravity is a conservative force. And since that is the only force that we're considering in this scenario, that would mean that all of the potential energy gets converted to kinetic energy and there's no loss. But let's confirm. Let's just see if our numbers make sense. So we know that kinetic energy is also equivalent to 1/2 mv squared. And so that'd be 1/2 mass, which is 3 times 10 to the 21 times 17,900 meters per second squared. Okay, so we have 1/2 and then the mass is 3 times 10 to the 21 here we get 4.81 times 10 to the 29. Okay, so which one do we use? Well, or why is there a difference in all of these numbers to begin with, particularly these two? Well, this is given to us as the parameters of the object itself. So we're given the object's mass and we're told its velocity. We're actually not told anything about the sun or anything like that. So this particular number ignores the effects of gravity, whereas this one accounts for the effects of gravity. And as you can see here, it's slightly larger because we're actually accounting for its interaction with the sun. And so, given this case, we were told that it converts all of its potential energy to the kinetic energy that it hits the Earth with. So we must go with this one. Okay? So I want to make it clear, this number that I have chosen, this kinetic energy accounts for the gravitational effects, the previous one where we just use 1/2 mv squared is the kinetic energy of the motion of the comet. Okay. If we were to subtract those two numbers, we would find that the gravitational energy that is provided in kinetic energy or converted into kinetic energy is that difference. So we now have a delta W because we were told that this whole quantity gets converted into kinetic energy. And we are told that that happens over a span of 1/2 second. Okay. And so then if we take this 6.3345 times 10 to the 29 and we multiply it by, or we divide it by 1/2 second, we see that we get 1.2669 times 10 to the 30. This would be watts. And so I just want to give you guys a physical let's see. Remember that a watt is equivalent to a joules per second. And what I want to show you guys is how many megatons of TNT this is, because it's a ginormous amount. And what we're going to say is that 1 megaton of TNT is equivalent to 4.184 times 10 to the 12 joules. So my math people out there that are very familiar with math can see that we have 10 to the 18 megatons of TNT. How did I get that? 1.2669. Let me make sure I get this. Let's just do this real quick. In fact, it is 3.027, let's just say 8 times 10 to the 17 megatons of TNT. Let's see, how many megatons of TNT are in a nuclear explosion? And as a comparison, our strongest nuclear bombs explode at 50 megatons of TNT. Which is like breathing stinky breath onto the impact of an asteroid on the Earth. I hope that you guys found this pretty helpful. We covered power, we dissected the equation, and we've learned how to use it. We also talked about some of the umbrella topics the topics underneath the umbrella of power. and we found, we used different types of work. We discovered that kinetic energy, uh, if we take into consideration only the motion of the object, we could get a different value of kinetic energy than if we considered the effects of other external forces like gravity. In fact, we saw that there was about a 2 times 10 to the 29 joule difference between the kinetic energy of motion and then the kinetic energy of gravitational forces with motion. Uh, if you have any further questions about this or anything, feel free to attend my coming office hours on Wednesday and Friday, 10 a.m. I will send out the link, and I hope you guys have a great day.